Hi everybody, so I'm going to introduce the second law of thermodynamics with a quick little video from YouTube. And then we're going to make a variety of statements of the second law because there are a number of different ways of saying it, which ultimately reduces to the same statement. It's not immediately obvious, but we'll just look at each statement in turn. There is a mathematical equation. We're not going to apply it a whole lot, but it is part of the curriculum, so I will explain it to you a little bit. So here we have a guy just standing here doing nothing, right? So if I play this, all of a sudden you see a fish jump up, okay, into his hands. And I want you to think about what's going on there, right? So let me there's a bunch of these. So let me do it again. And boom. So imagine not just a fish, any object were to leave the ground and jump up to your hand. And yes, what's going on? How was he able to do that? Is there magic going on there? And obviously you know that's not the case. You can probably figure it out that how we're seeing there is just running whatever video he made backwards. Okay, so why is it that if we set aside the idea of magic or something mystical going on, that this is just a film running backwards? Why don't we ever see this in real life? What laws of physics is this violating? Okay, well, it's not immediately obvious what laws of physics this is violating, because it is not violating the law of conservation of energy. You could argue that the fish got internal energy from the surroundings that all came together and gave enough energy to lift it up to give it potential energy. Okay, there's no violation of conservation of energy there. We understand that if we drop the fish on the ground, all that potential goes into thermal or internal energy to the environment. So why can't you reverse that? Well, conservation energy says that's not a problem. Yet we almost never, in fact, we never see that. So that when we see a video of what seems to be impossible, we assume that some shenanigans are going on here. But we need to ultimately explain that in terms of a law of physics, and that's where the second law of thermodynamics comes in. Okay, so I'm going to get to that eventually. I might not address what we just showed you directly, but it turns out it's a very, very fundamental and important idea. Okay, so let me just jump into the second law of thermodynamics and the many ways of stating it. Okay, and ultimately they're saying the same thing. How well a job I do of explaining that, how the same thing is, well, I'll let you decide. Okay, so let's start with the simplest statement, and I kind of did this in tongue-in-cheek, like commandments. So the first one is from hot to cold. Heat shelf spontaneous flow, and spontaneous is important there. Okay, we've already discussed many times that if you put two different bodies in contact, let's say, where one is hotter than the other, there will be this process called heat flow, and it will go from the hot body to the cold body, always spontaneously. Okay, if you want to do the reverse, you have to put in work to do that. All right. In other words, a refrigerator does the reverse, an air conditioner does the reverse, but those don't just run on their own. You got to plug them in, and there's a compressor or some motor in there that is doing the work that make the heat flow the wrong way. So this is one aspect of the second law of thermodynamics. You can't, and we saw that with heat engines, you can't get heat to do work for you unless there is a hot, right? We have a QH that goes into W, but there's got to be a QL, okay? And so that's spontaneous. That's one aspect of the second law. All right. As a consequence of that, we have another statement of the second law that no device shall transform thy heat completely to work, right? We see that right there. And that's the necessity of a cold reservoir. So we came up with an equation that says, all right, the efficiency of a system is how much work I get out of it divided by the QH. And then the best we can get, the Carnot efficiency, turns out to be really 1 minus T, let me see if I get this right, cold over TH. Right? It's, in other words, the bigger the temperature difference you have, the more efficient it is, but that's the ideal. And so this is the maximum. You cannot exceed that. So this is basically saying this can never exceed that. And because it can't exceed that, we get this statement that you can never ever turn all your internal energy into work. Okay, now we can start relating this to the idea of disorder. So another important statement of the second law of thermodynamics, which ultimately ties in with the two I just mentioned, is nature shall spontaneously, and again, that word spontaneously is important, move from an ordered state to that of disorder. Okay, and this is kind of misleading. It's more complicated, so I put that little disclaimer there, and I'll also get in a minute. But one way we can look at why nature spontaneously moves from order to disorder is a simple matter of probability. Okay, and we're going to talk about how probability relates to this very abstract concept called entropy. So here is a little diagram that maybe best illustrates it. Take a box that has, let's say, 10,000 molecules in it, right? And look at all the different ways that those molecules can be arranged, right? So those are three such arrangements. Ask yourself, how many different ways could you arrange those 10,000 molecules, and what arrangement would most likely come up? I think it's pretty easy to understand that to have them all clustered here or here or here or here or here, there are certainly a number of ways you could do that, but it's fairly small. Whereas the number of ways I could arrange 10,000 molecules in a more or less random pattern is astronomically larger than what I can do where they're highly ordered or clustered. So in other words, where we have a clustered arrangement of particles without actually ordering them ourselves, we're not inputting energy, this is very low probability. This is moderate probability. This is very high probability. So we see down here that our entropy is increasing. All right, and another way you can look at this, take a snowflake. Okay, so you have a snowflake which is a highly ordered arrangement of ice molecules. If you leave this alone, spontaneously it will go to more disorder. In other words, random molecules in a vapor or even water state. Okay, so in this case what we see, and it's hard to see here, is the total entropy change of the system has increased. In other words, it's greater than zero. And that's a really, really important statement. Okay, so generally we associate entropy as with disorder. Okay, but that's not technically right. More accurate to express it in terms of something called degrees of freedom. I'm not going to go into that detail, but the more freedom you give a molecule or a system of molecules to jiggle or move whatever way, then nature is going to move towards that spontaneously. Okay, and so there are some systems where you can have more ordered arrangements of molecules because you're increasing the degrees of freedom. I don't know if I have a video that shows that in more detail. So I just want to put up a disclaimer is disorder does not always mean greater increase in entropy. Okay, so the very interesting is that this idea of entropy and order or degrees of freedom is an important basis for the origins of life. Okay, because if you look at any living organism, it's something as simple as a bacteria that's highly ordered. And then you would think, well, there's no way nature would spontaneously move from a disordered random molecules to something that's ordered and carrying out certain processes. But this degrees of freedom aspect is you can get more order and yet increase entropy. Okay, and there's more to it than that, but we want to understand that if you hear arguments against life spontaneously forming because that goes against the laws of entropy, that's not quite right. So there is an equation for entropy. It's not a difficult one. Well, it's not a complicated one, but it's not easy to apply. So entropy is given a symbol S, and what we're interested in ultimately is the change in entropy of a system, okay, not just the entropy itself. And that's by definition Q, and Q is really the heat that flows in. So that's usually a positive Q divided by temperature. And usually when we apply this equation, the temperature has to stay the same during the Q flow. In other words, that corresponds to a phase change. If we're actually talking about temperature changing, you need calculus. But we can do simple approximations if the temperature change is small, and I'll do a quick example in a minute. There is a more subtle version called Boltzmann's, and I'm just pointing this out. It's not in the curriculum. That the entropy is Boltzmann's constant, so there's that really important constant again, times the natural log of W. And W doesn't work here, but it's really your degrees of freedom. So how many different ways you can allow something to, well, I'll say move, but that's not quite what degrees of freedom are. So there's an interesting way of doing that. I'll leave that alone for there. Okay, so let's show mathematically that entropy increases when heat flows from hot to cold, right? That was our first statement of the second law of thermodynamics. And then another more complicated abstract statement is this idea of entropy always increases when you have a spontaneous process. Okay, so what we have is the entropy of the whole environment, not just a particular object. So let's say, let me just draw a simple schematic. So I've got some system where I've got a hot and then I've got a cold part, and we know that there's going to be Q flow from hot to cold spontaneously. So let's show mathematically why the delta S has to be positive. So the delta S is going to be equal to, so I'm going to have a change in entropy as we go from hot to cold. In other words, the part of the system that loses thermal energy, and we're going to have a change in entropy for the part that gains it. So there's going to be two parts to this. There's delta SH plus delta S cold, okay? So imagine I took a warm piece of metal, put it in water that is cooler until they reach equilibrium. So this one is, we're going to have in the hot part of the system, heat is going to flow out of that. So we're going to have negative Q, and that's going to be occurring over a more warm, I'm going to call it TH temperature. So even though the temperature is changing, if we look at the average temperature, let's say the temperature goes from 100 degrees Celsius to 80 degrees Celsius. We'll look at the average temperature of that, but I'll just call that TH. And then for the cold system, heat is going to flow in, so we're going to get positive Q and over the average temperature of that cold part of the system. Well, we can deduce that we know that Q, negative Q equals positive Q. In other words, the heat that flows in one equals the heat that flows out of the other. So the values of the Q's are the same in those. But we know that TH on average is greater than TC. Even though they reach the same equilibrium temperature, the temperature of the part of the system that was warm is going to be greater than the one that was cold. So in other words, this negative value is going to have, take away the negative, we can say that delta, I can say, it's awkward because of the mathematics, delta SH is less than delta SC, okay? And so therefore, the negative part of this is smaller than the positive part of that. Well, of course, negative is smaller than positive, so that's what I mean. But when I add it together, I'm going to get a positive delta S overall. And that's what the second law of thermodynamics says, is that the total entropy for a spontaneous one is always greater, or always increases. Okay, so let's finish up here. So as a consequence of this, when thou does useful work, some will forever be shamed to degraded energy. So this is a really important statement, is that we talk about energy crisis. It's not that we're running out of energy. We're running out of useful energy, because when you burn something, you're taking ordered energy and you're making it more disordered. And this is getting back to that original video I showed you where we had the fish jumping up the hand. We know that just doesn't happen, even though that doesn't violate any conservation energy law. So solar energy, foods and fuel, kinetic energy, think of an object moving forward, or potential energy are all highly ordered. Okay? So in other words, in a kinetic energy of an object, all the molecules are moving in the same direction with the object. In foods and fuel, you have molecules arranged in such a way that the potential you have there is due to that arrangement of molecules and the forces between them. Okay? So in other words, they are low entropy because they're highly ordered. Whereas thermal energy is the exact opposite. It is highly disordered, because thermal energy, you have the molecules moving in every which way randomly. And think of the ideal gas. And this is the entire basis for our civilization's continued energy crisis. Okay, we're not running out of energy. It's that less and less of it is useful. Okay, hence the importance of renewable energy sources, because renewable energy sources ultimately, especially coming from the sun is highly ordered energy, and so we can replenish all that energy that's becoming disordered when we burn fuels, etc., etc. So I'll continue this in the next tutorial.